Hi, Carter. Anyway, what I do want to show is I want to share my screen now, and then I think I'm going to share an application, and then what you're going to be, holy cow, why is it happening? I don't want that. But anyway, I can't go to one of them. Sharing an application, so stop, I gotta stop sharing. Let me try that again. Share application, content. I think this one is the one I want. How's that? Is that better? Okay. So then we go down to Blackboard Collaborate Ultra. All right, this is your course, right? We are in session on Rocktober 6th. I have not, but we have a lot of them. But so you're like, well, gee whiz, there's something we did on limits that I really would like some extra help on. You can go back. If you notice, I just click in the 3 lines in the upper left corner, and it brings back all the recordings. Did you know that was there? Okay, now you know. So then you hit, this would have been great for reviewing for the quiz. Anyway, so and then you can just watch now, and then all of a sudden, like, you're gonna notice it loads the recording, and then it's gonna be what we did before, which I'm not gonna do that. All right, so I'm gonna stop sharing that screen. We're gonna go back here. Now I can share my whiteboard and go from there. So I really can't, right? But we're looking at continuity, right? So what is continuity at a point? We need 3 things. F is continuous at x equals a, at a point. If and only if 3 things happen. So name one. First thing, somebody was here yesterday. Anybody? I'm going to pick on everybody. Kylie. The first thing for continuity at a point, what do you have to have? F is continuous at x equals a, if and only if the following 3 things hold. F at a must what? Exists, right? So in other words, we actually are defined at x equals a. That we did not need that for limits, right? What we have now. Second thing, Isaac. From both sides. Remember, that's from both sides, right? So this also exists. And then the last thing, John. The first 2 are equal. 1 equals 2. So in other words, the limit as x approaches a from both sides of f of x. The height we approach from both sides is actually going to be the height that it is defined at. Okay. So basically, what we're going to be able to do is we're going to be able to draw our graph through the point. Okay. So if this is our function, there's f of a right there, af of a, but we're going to be able to draw the graph through that point without lifting our pen. Okay, so ultimately what we notice is that there's no holes, there's no hole there, there's no rip or jump or tear is another slang for that. There's no rip, jump, tear there. There's no stop at that point. So we go through it, not to it, right? Just like tackling drills, hit through them, not to them, keep your feet going. By the way, did you know that that's how you block with your feet? Whether you're a receiver or lineman, you block with your feet, you keep your feet going. You know that? Okay. Like everybody knows that? Okay. So, because sometimes I see people tackle and block and not keep their feet going. But anyway, it's a learned trait. All right, any questions on that? Okay. And then what? So that's at a point, right? And we looked, I can't remember, I just remind me what we looked at. I drew some pictures, right, before. So you can look back at those pictures on what is and isn't continuous, correct? ultimately, the concept, if you have the graph, is you can draw the graph through the point. Then, what do we have? Did I do a specific one like x squared? I can't remember what I did before your quiz. Somebody have notes? Like one person took notes? Thanks, Lou. Did I have x squared? F of x equals x squared example or not? I didn't get to that? So let's look at an example. Fine. All right. So here's an example. If we have show f of x equals x squared is continuous at, pick a point, any point. What point do you want? At x equals 2? Now we know what the graph looks like, right? So let's just look at the graph, and we know it's y equals x squared is a parabola, right? So, and then over at 2, I'm up at 4, right? So the limit that we're approaching, f of 2 equals 4. So we just need to show 3 bullets. So the first thing is we need to show f of 2 exists. What is f of 2? Well, it's 2 squared, which is 4, right? So that exists. So I'll just put a check mark there. Second thing, we need to look at the limit as x approaches 2 of f of x, which is x squared, right? Well, what was that? Limit of the exponent is the exponent of the limit. After it's a polynomial. So we said if it's a polynomial, we can just plug in, right? So since it's polynomial, that's just 2 squared, which is 4, right? So that exists. And not only that, but then bullet point 3, 1 equals 2. Okay, so we have the 3 requirements. Make sense? Pretty simple deal. In fact, we can pick any point A, and f of a is going to equal to a squared, and the limit as x approaches a of x squared is a squared, and they're going to be continuous at every point. So if I do that, let me just, instead of writing it out, instead of x equals 2, let's do x equals a. So a is just any point. Okay. Well, what would f of a be? F of a would equal a squared, right? So that exists, right? Because a is some number, so a squared is some number. The limit as x approaches a of x squared is a squared, right? And they're equal. So we have the 3 bullet points. So it's continuous at every point A in the domain. So then that comes to what is called a continuous function. So because of the red here, therefore, f is continuous on its domain or on all real numbers, right? Because if we let a be an element of the real number, so a is an element of the real numbers, which is the domain of f. So we knew that the domain of f was all real numbers, right? Because it's polynomial. Domain of f was all real numbers. We pick any real number and we show it's continuous at that point. So it's continuous on its domain. That's how we say that. All right. Let's look at, you have your book, and I know that, so if you look into section 1.7, let's look at number 7. So this is back in limits, but I think I looked at this one for some reason. I don't know why I looked at that. Never mind. All right, move on. We're in 1.8 anyway, 1.8. So that's a definition. Let's just do definition. So DEF definition. Man, F is continuous. F is continuous. Is a continuous function. So it's a continuous function if and only if f is continuous at every point in its domain. Wow, that is, I hate this. This is like a slippery board. F is continuous at every point in its domain. So it's called a continuous function. So how else could we say it's continuous at every point in its domain, or it's the other way we could say that f is continuous on its domain. That makes sense? So let's look at an example. Let's look at one that's not quite so evident. So let's look at an example. Let's look at f of x equals the square root of x. Okay. First of all, is this continuous at x equals 0? And what would you say? Yes or no? What's the first thing? What's f of 0? Does that exist? What is it? Go ahead. Chime in. Go ahead and talk yet. Jordan? Yeah, what's f of 0? So we got 3 bullet points. First one is f of 0 has to exist. What is f of 0? Square root of 0, which is 0, right? So is that okay? Everybody agree? Square root of 0 is 0, so it exists, right? So bullet point 1 is fine. And then bullet point 2 says we've got the limit as x approaches 0 of the square root of x, f of x. That also has to exist, does it? Why? It does not, yeah, correct. So this does not exist because if I look at the, let me change colors here. Red is right. So if I look at the right-handed limit, that'd be limit as x approaches 0 from the right of the square root of x, which would be the square root of a tiny positive number, right? Which actually equals 0. So the right-handed limit exists. However, the left-handed limit, and we'll use blue for left-handed limit, the limit as x approaches 0 from the left of the square root of x would be essentially the square root of a negative tiny number, which does not exist, right? So, so therefore, the limit as x approaches 0 from both sides does not exist. So 2 fails. So it's not continuous. So the answer is continuous at x equals 0. The answer is no, correct? Okay, now I'll give you a little hint. Just like in limit theory, we talked about limit as you approach a point from both sides, but then we also looked at right-handed, let's see which one's your right, right-handed limit and left-handed limit. We're also going to look at right-handed continuity and left-handed continuity. So it's actually going to be the case for the square root, and I'll graph it. We all know what the square root looks like. But what we're going to say at 0, at x equals 0, that we're going to have right-handed continuity at, we are going to have right-handed continuity at x equals 0. And we're going to have both right and left-handed continuity at any point bigger than 0, right? Because you could actually approach from both sides and be fine. And we don't have continuity for any negative number, right? Because you don't even exist. F of any negative number, square root of any negative number doesn't exist, right? But does that make sense? So just like we had right and left-handed limits, we're going to have right and left-handed continuity. And so that's coming down the pike. So what we can say with this so far is it is going to be continuous. It is continuous. This function is continuous on the positive reals, right? For sure, which is not including 0 to infinity. However, we're gonna clarify that, and what we're gonna end up doing is say we're actually gonna say, hey, this is actually continuous on including 0 to infinity because we can show right-handed continuity at the start point, and then ultimately that's the domain, right? So eventually we're gonna say, yeah, hey, f of x equals the square root of x is a continuous function because it's continuous for every positive number and it has right-handed continuity at 0. Okay, just to let you know what's coming. By the way, when we get into calculus in chapter 2, we do a thing called a derivative. That's really where this is just all the beginning stuff that leads into a derivative, which is instantaneous rate of change, right? And we're going to have a right-handed derivative and a left-handed derivative. Isn't that cool? So like a lot of this stuff is similar concepts over and over again, but they're just, you know, looking at things a little bit different way. All right. And moving on, let's look at oh, by the way, yeah, it would be, I think that's section 1.9 that we get into one-sided continuity. All right, let's look at this one. Wait, let's just example. Let's look at a polynomial function. What's a polynomial function look like? We're going to call it p of x instead of f of x. It doesn't really matter if you call it f or p or g, but I'm going to call it p of x. Well, that's just a sub n x to the nth power plus a sub n minus 1 times x to the n minus 1 power plus all the way down to a sub 2 x squared plus a 1x plus a sub 0. Right? That's polynomial function. What do you know about polynomial functions? Are they going to be continuous at any, what is their domain? Domain of a polynomial function is all real numbers, right? Are they going to be continuous at any point? Yeah, because if you plug in, let's just say x equals a. By the way, a sub 0 is not the same as a. Could be a different number. A is any point, any real number. So if you wanted to do the 3 bullet points, f of a exists, it'd be a sub n a to the nth power plus a sub n minus 1 a to the n minus 1 power, right? You can do that. So it exists because you can just plug in that point. And not only that, but the limit as you approach a from both sides is the same outcome. Because what did we say for limit theory with the polynomial? All those theorems that we had, you can just plug in the point, right? And then 1 equals 2. So you got the 3 bullet points at any point. So our theorem is, or our result is, this polynomial functions are continuous on their domain or continuous on R, which means they're a continuous function. Another way to say that is any polynomial is going to be a continuous function because it's continuous on its domain. Okay, so if a function is continuous at every point in its domain, then it's called a continuous function. That was a definition I gave you a little bit earlier, right? If you don't believe me, check the film. Check the tape. Is this on tape? This is on videotape, right? Is it VHS or beta? You love when your parents are like, hey, we should tape that football game. Your parents still say that? Nobody's trying. Do they say record? I know my dad says tape. Hey, we can tape it. No, you can't. You got to DVR it. You didn't know what that means. All right, let's look at an example. Technology changes, man. Back when I was a kid, you just used to wait for the rerun to see if you wanted to see it again. All right, f of x equals. But with this set, I can be teaching from the grave. It's awesome. All right. Let's look at 1 if x is greater than 0. Let's let it be 0 if x equals 0. And let's let it equal -1 if x is less than 0. All right, let's just look at that real quick. So what's that look like? Well, we can use different colors here if you want. If x equals 1, it looks like that. Boom, right? The red. Constant height of 1. What about f of x equals 0 if x equals 0? Well, that's the origin, right? 0, 0 is on your graph. And then the other one, we'll use purple here. All right? Basically, it's that, right? So if height's 1, if you don't see tick marks, the heights we go by ones. But anyway, there's 1, there's -1 for heights. We're good? Everybody good? Where is this continuous? What might be easier to say, where is it not continuous? Or where does it have a discontinuity? At x equals 0, right? Why? So it's discontinuous at x equals 0. Why is that? Well, what fails? F of 0 equals 0, right? So that's okay. But the second point, the limit as x approaches 0 from both sides of f of x does exist. So 2 fails. 2 fails. right? So as long as you have at least one of the 3 bullet points failing, then it would be discontinuous at that point. So this is discontinuous at x equals 0. What about any other point? It's going to be continuous at any other point. If a is some positive number, right? And I'll go ahead and we'll just draw that. Now remember, a could be really close to the origin, but it doesn't matter because you could zoom in because there's infinitely many numbers between a and the origin, right? So you could zoom in, so we could take any open interval and we could approach from the left and from the right there, and then we're going to end up the limit as x approaches a from both sides is actually equal to 1, which is what f of a is, right? So 1 and 2 and 3 bullet points are all going to be the same. I could also do that on the left side. If I have some other point a, basically I can take some window around a, and as I approach a from both sides, the limit as x approaches a from both sides also exists and equals -1, which is f of a, and for that point, right? So basically I am continuous everywhere else. So let's write that down. So continuous everywhere else. Where's that? So everywhere else. So give me where it is continuous then. Give me interval notation. Who haven't I picked on yet? Jack. Hey, Hannah and Luke, Jack was like ready to beat me up yesterday because I called him a juvenile. Well, I called everybody a juvenile. Yep. What intervals for continuity would we have here? If you give me an intervals where it is continuous.
So negative infinity to zero.
Do you include 0 though? No, because we just showed us discontinuous 0. Union.
0 to.
Okay, so the way that you would want to say that is not including 0 to infinity. Union, not including 0 to infinity. By the way, for the record on film, what does juvenile mean? We learned yesterday. Hannah, do you know? It means young person. It means young person. But if you put something slanderous like delinquent afterwards, then we can get mad, right? Because we're good people. Whoa! Where'd that come from? Cancel. All right, anyway, so how else, what's the shorthand way to write this? I could say the negative reals, remember that, union the positive reals. So I could show it like that, I could show it like this. How else could I show it? There's one other way to show this. All reals excluding the set containing 0. Remember, capital bold letters are sets, so I have to put set braces around the 0. So all reals excluding 0. My head's not like my shadow. Like I got big hair going. I haven't cut my hair in like 3 months, but anyway, starting to irritate my family, so it makes me want to keep growing it. You know what I'm talking about. Huh? Yeah. By the way, here's a question for you, since I'm on film and everything's recorded. But when you think of somebody that's macho, true or false? They have back hair, right? Do they? You think? Yeah. Well, apparently my wife does. She called me macho. I'm like, how can I be macho? I don't have any back hair. And she's like, well, I didn't think of that. I don't know. Everybody's interpretations of everything is different except calculus, which is pure and God's math. And don't even question that, because I had a conversation literally at the same time talking guardian angels with Father Bain. I let him know that calculus was God's math because he stopped at pre-calc. And I said, well, somebody should have told you that the only reason to take pre-calc is to take calculus. He's like, well, they might have told me that. But anyway, so I'm going to teach him some calc. He's going to teach me about the afterlife. All right. Whoa, why did I stop? Hi, Carter. You can say hi. I didn't stop recording though, right? Okay. Whew. Thank goodness. Carter, don't laugh. It might hurt. Can you say hi to us?
Hi.
Hey, that worked out pretty good. We don't have that feedback. Maybe I should be the one that stays home and you guys all show up to class. Oh, wait, I did that for a couple weeks. I forgot. All right, anyway. Share application. Do you have any other professor or teachers at Yale?
Mr. Kane used to all of them.
Yeah.
That's what you would always tell over here, it's not the same. It never is so loud.
With formula 409, that is dangerous. Oh, all right. Wait a minute. Stop it.
Nothing's got really good range.
Share whiteboard, blank whiteboard.
Were those Mario bubbles or- Those were wicked.
Hey, Carter, were you on when I said, hi, Carter? Look, I can see myself in back.
I think so.
Oh, you can't see it. There we go. Hi, Carter. All right.
Hi.
They were like really hard.
Whiteboard. Okay, and then we got to talk about, hey, okay, rezone in. We got to talk about a discontinuity. Why'd you leave? Oh. A discontinuity is removable. All right, we got to be careful how we spell this. Removable if discontinuity, by the way, at a point, at x equals a, at a specific point, is removable if redefining that point would fix the discontinuity. If we redefining the point a f of a would fix the discontinuity. So what does that mean? It would make it continuous. Correct. So how can we do that? Give me an example of what a graph might look like that's discontinuous that we could fix. Could we fix that? How could you redefine it at 0? Well, if you redefine it, it's still going to be discontinuous at 0. You can only have one height. You're talking about the flat lines at different heights. So there's no way we can fix that one. So that's actually going to be an essential discontinuity. But example of this would be fill the hole. So we can fill the hole. So if we have a hole in our graph and we fill it, then we can fix it. Then that'd be removable. So let's look at an example. What was the one on your quiz? X squared minus 4 over x minus 2. So let's just look at that. X squared minus 4 over x minus 2. That's a discontinuity. Or what? It was 9 and 3, wasn't it? Wait a minute. It was 9 and 3. And number 1 on your quiz. I don't know. I think it was this. But then what's the domain of f? All reals except set containing 3, right? And the range is all reals except. So like it was a line. Boy, some of you, my lines aren't very straight, but some of your lines are bad. I'm not gonna mention any names. I'll just stare at some of you. But anyway. All right. Anyway, so we have this, right? But we have a hole. So basically, this is continuous on its domain, right? Isn't it? Isn't it continuous on its domain? It's continuous everywhere except at x equals 3. So this is actually a continuous function, right? Technically, we could say this is a continuous function because it's continuous on its domain of all reals excluding 3. But at x equals 3, we have a removable discontinuity. Why? What can we do? By the way, that doesn't make it a continuous function just because it's removable. It's a continuous function because it's continuous at every point in its domain, right? So you got to get with the lingo there. But what can I redefine f of 3 to equal? Fill the hole. How can I make, why is it continuous? I could redefine f of 3 to equal what? 6. See that hole? Now I can draw my graph without lifting my pen, right? But if I redefine f of 3 to equal 6, it fills the hole, which removes that discontinuity. So I can say it was discontinuous. This function, original function, is discontinuous at x equals 3, right? Everybody agrees, right? Because there's a hole, f of 3 doesn't even exist. So 1 fails, right? Bullet point number 1 fails. So it's discontinuous at x equals 3. However, this function, this blue function, is a continuous function because it's continuous at every point in its domain, which doesn't include 3. So we can also say it's discontinuous where the hole is, so it's discontinuous at x equals 3. And we can also furthermore say, what is that light? But we could furthermore say that f of 3, or excuse me, x equals 3 is a removable discontinuity because I could redefine it in a way that fills the hole or that makes it continuous at that point, right? So it's a removable discontinuity. So that's a removable discontinuity. Now let's go back and let's talk about essential discontinuity. F has an essential discontinuity at x equals a if redefining, if and only if, so definitions go both ways. If and only if redefining it at x equals a cannot fix the discontinuity. And so really what we have here, so example, if we have a rip or jump or tear, however you want to think about that. So that example that we had before, which was this, right? This is an essential discontinuity at x equals 0, right? So that's essential. So you can't fix it. Okay? So everybody good with that? And just to finish up real quick, so we already said that, got 1 minute, no questions? Okay, so that is the removable discontinuity that I just talked about. Oh, she's Irish and she's gorgeous. Shoot, I'm still on film. I gotta start. Lisa knows about her. It's all right. Okay. Anyway, my girlfriend's theory. All right, but anyway, so if I have q of x, some rational function, rational means divide, right? So rational functions, q of x is n of x divided by d of x, where n of x and d of x are polys, right? So the domain of q is the set of all x's such that d of x, your denominator, does not equal 0. That's an easy way to say that. You could also write it out in words. So basically the domain of q is a set of all x's where your denominator does not equal 0, right? Because you can never, ever divide by 0. But anyway, this function, these functions, these rational functions, q of x, are continuous on their domain. So for any point in the domain, they're going to be continuous. Therefore, it's a continuous, these are continuous functions. Okay, so we got to get used to the lingo. So read in your book, 1.8, work the exercises, try to have the evens done. Let me see if I've given you enough. I think I'm talking about show where it's continuous and state the reason, blah, blah, blah. I think we're good. The only thing I haven't done is epsilon delta for continuity. I don't think you need that. There's a couple other results that we have. I haven't done epsilon delta, but do everything that's not epsilon delta, including the evens that I want you to turn in. And work on some on continuity if I've covered it.
Is it, let's do, that was due on September 30th.